So yesterday we learned Demoivre's theorem, which I'm just putting in this box again. You have it already in your notes. We also want to recall, just for the purpose of today, the fundamental theorem of algebra from the first semester, which says this. So it makes sense that we expect from a problem like the warm-up today, which we were asking for the solutions to a cubic, we expect there to be 3 solutions, some of which may be non-real, like we just saw in the warm-up, right? We got 1 real solution and 2 non-real solutions. So we're going to combine these results to help us think about how to find the nth roots of any given complex number today. Okay? So that's the goal. And the activity in front of you is going to help us do that. Not just find them, but also help you visualize them. You may want to get your calculator, have it at the ready for what we're about to do. But let me walk through the theory first. Okay, so at the top of the page it says the equation that we're going to be solving and visualizing the roots of first is this one right here. Z to the 5th equals 32. Negative 32, excuse me. Okay. And then it says, well, that's, or you could write that in this form, sure. So far so good? Most often we've also been writing it in polar form too. So we said, well actually, another way of writing this would be in polar form. It would be 32 cis 180. If we're going to use degrees today, but or 32 cis 180, 32 cis pi. You like? Yeah? Is that okay? We haven't lost anyone yet. But just to be clear, you could have picked 180. But what else could you have picked as an angle there? What other angles would work?
3 pi.
What's 180 plus? Yeah, 3 pi. As you see, much easier radians, right? Or how about let's actually not figure it out. Let's just say 180 plus 360. Do you agree that that would also be a good name for this point too, if you wanted to write that instead?
Yeah.
Right. Or actually, let's to be really pedantic here. Let's do also that, yes. Or actually, just to be really clear, 360 times any integer. We could add 360, as many copies of 360 as we like. Okay. So I know this seems strange, but let's write this as the polar form, where n is 0 or whatever other integer you like would give a correct polar form. All right, and then it next says, what must, if we're trying to apply Demoivre's here, it says, now, where are we on this? I'm trying to track with this here. It says 1, okay, that we just said that. Okay, by Demoivre's z to the 5th equals r to the 5th cis 5 theta for some r and some theta. So tell me, what is r? What must r be? We're matching this up. So certainly r is 2. And what is theta? Well, or at least 5 theta must be 180 plus 360 times n, right? So what must theta be? Well, of course, so you're tracking with the first 4 things on the sheet there? Those number 1, 2, 3, and 4 that come to this conclusion for this problem? Okay. So now, it might seem a little weird to say this, but if n is 0, we get a correct angle. If n is 1, we get another correct angle. If n is 2, etc. Now, on there, they have it replaced with t. But that's because we're about to head to the calculator and do something. Visualize a complex plane with parametric coordinates. So what we're going to be looking at is a little bit of, maybe, I don't know, it's not a lie, but it's a little bit of maybe of a lie, I don't know. But we're trying to convince ourselves that like the parametric coordinate system, we're going to use that as a complex plane. Okay? So we're going to try and not just have the roots, but also visualize them. So go ahead and start putting in your calculator in all these things that says these modes. Put it in parametric mode. I'll come up with my calculator to it too. Make sure it's a degree mode. Enter in x1 and y1 on your calculator in parametric mode those 2 equations. And when you go to window, you understand the t, x, and y parameters down there? Look at that, right? So that's the t min, t max, t step. X min, x max, x step. Y min, y max, y step. Right, so get your calculator all queued up, type all that in, just as you see it, so you can think, you can figure out why we're writing that too. I'll pull up my calculator. And when all is said and done, when you hit graph, see if you don't get, see if we can all get that picture on our calculator that you see there. Yeah? How you doing out there? Why is the t step 1? Why is the t step 1? Do you see? Are you obeying all this? You see that the t step is 1 in order to get this picture? What happens if the t step is something like we normally use, like 0.1 or 0.01 or something small? We usually like make the t step really small. It makes it curvy. Let's be more specific. In this case, it would be what? Yeah, it would be a circle. You can feel free to make that momentary mistake, put it in there, and you'll get a circle. But that's not what we want, because we're having t here act like an integer, right? So let's let t step be 1. That's what it says on there, but I just want to make sure you understand why t step being 1 is a good choice based on the model we're trying to build. Did you get the picture? What are you looking at? Once you get the picture, try and figure out what exactly did we just do? What are we looking at, actually? This is the complex plane, I guess. Real axis, imaginary axis. What's the leftmost point in the picture? What point is that? What's its name? Real axis, imaginary axis. So that's -2. There it is, -2, comma 0. So as you fill in your table, go ahead and do it. One of them, the third root in your table, or the whatever, 0, 1, 2. Or when t is 2. When t is 2, you're here. You get for x -2, for y 0, and then we're treating that as just the rectangular form of this point. So we want to write -2 plus 0i. In the next column there, where it asks you for the rectangular form. Do that for the other ones too, right? So that for the very first entry in your table, you'll use this point right here, 1.618, and for y 1.18, right? And then in the next column, you'll write, for the complex number in rectangular form, you'll write 1.62 times plus 1.18i. You with me on this? X is the real part, y is the imaginary part here. Anyone recognize the x component? Yeah, it's the golden ratio. That's because we're looking at a pentagon, and the pentagon has all sorts of golden ratio-ness happening inside of it. So yeah, keep doing that. Now, what about the last column? What does it ask for? It asks for the polar form. So one way you could get that is by doing what we always do, we kind of convert it, find, okay. Or you can use, I don't know, does it say it on this? Use polar grid coordinates? So here's a really fast and fun way to do it. Go second zoom, to your format menu, and then instead of rectangular grid coordinates, pick polar grid coordinates. And now when you trace here, look what it says. So what number, what are we calling in the last column of the first row? What are you writing? You're writing 2 cis 36 degrees, right? You got to put it in polar grid coordinates, and you get there 2 cis 108. This one's not a surprise, 2 cis 180, right? So you can be with me on this. So filling out the table. When you're ready, go on to number 4, and when you're ready, go on to number 5, and see if you can adjust what we've just done, see if you understand it well enough to modify it for a completely different problem. You go to second zoom to the format menu and choose polar GC. Open up. You have a circle too? Why do you get a circle? Yeah, make sure your window is what it says. How's it going? You draw up the table? People on number 4, at least. Number 5.
Oh, right. I was thinking
How do you get it to close off? Did you figure that out? Yeah, let's make t equal something 5 or bigger. I put it up to 9 so you can see here. If you keep going up higher, of course, it just keeps repeating these points, right? Or you can just put it up to t equals 5 and you'll be to where you go. Anyway, that's good. You'll be making all sorts of regular polygons now. What's the one you're working on number 5 going to be? Yeah, I think you should get a triangle on that one. If you can at least finish 5 in the next couple minutes, I'd like to bring us back together then after you do 5. Find the 3 roots of 27?
Yeah, I don't know.
So what's one of them?
3.
Of course, yeah, 3. What's one of the other ones?
Negative 3 plus 3i root 3 over 2.
Negative 3 plus.
3i root 3 over 2.
Yeah, yeah. So 3. Negative 3 has plus or minus 3 root 3 over 2 times I. Something like that. Plus or minus, yeah. You get both of those right. Yeah, in fact, actually, this sounds a little familiar here. I'm going to go back and we're going to do the warm-up again. Okay. Now this, let's just be clear. This is different than the problem you just did. You just solved, if you're doing the triangle one on number 5, you just solved z cubed equals positive 27. Yes? That's a little different. You can go with it. All right, so here we go. I just want to walk nice and slowly through how you might do this. Here we go. So z cubed equals negative 27. Now, I just want to make sure you're clear. In the future, as we move forward with this, we're not using the calculator. We're going to use, just think about the way we've just been doing it here. So we'll write this maybe first in polar form. So that's 27 cis pi. Agree? Isn't 27 units in the pi direction a good description for our number? Okay. But we've already said over on the board and earlier our discussion said pi or anything coterminal to that, right? So I think we're set now. Now we'll take the cube root. So we get all of this to the 1/3 if you want. And in so 27 to the 1/3 is 3. But Demavs would ask us to do what inside here? Yeah, multiply by 1/3 or divide by 3. Right? So now I mean, in some ways we're done. We just need to kind of unpack what we've just written down. If n is 0, we have 3 cis as one of our roots. 3 cis. If n is 0, just 3 cis. Yeah, pi over 3. If n is 1, we get what? 3 cis. If n is 1, we get pi plus 2 pi on top. 3 pi over 3, which is pi. And that one actually should not be a huge surprise to us. What's 3 cis pi? It's -3, right? Which is a solution before you even started that you knew. N equals 2, we should do as well. What do we get there? 3 cis. Not all of them. 5 pi over 3. Right? And if you do n equals 3, what do you get? 7 pi over 3. But what's that? That's just coterminal to the original one. So it's not, you can keep doing them, but you'll just get the same answers. Okay, so but that's good. We only expected 3. That's all we're asking for in life. So let's actually do these out here. So here we have 3 times, what's the cosine of pi over 3? What's the sine of pi over 3? Let's write this out. We get cosine of pi over 3 is plus √3 over 2 I. This one we can just right away just write down -3 if you like. And over here we have 3 times cosine of 5 pi over 3, still a half. This time minus √3 over 2 times I. So this is the kind of work I would expect here. Our final answers are 3/2 plus 3√3 over 2 times I, -3, and 3/2 minus 3√3 over 2 I. Do those look familiar? Zach? Right? Those are the same answers we got for the warm-up, right? This is the warm-up problem just again. Okay, but using a different approach, hopefully they agree. But of course we'd like to be able to do this for even higher powers and more, right? Where the warm-up technique maybe doesn't work, or for stranger complex numbers. So the technique here is, I just want to make sure you're clear, the technique is to put our number into polar form and then apply Demavs, and really that's the whole story, with one very, very large footnote, and that is, please be very careful to understand that if you don't have this plus 2 pi n, you'll only get one root, and you won't get the rest, right? So we need to have that plus 2 pi n in at the beginning. So visually what's happening here for this one, we get -3, we get 3/2 plus 3√3 over 2i, and 3/2 minus √3 over 2, 3√3 over 2i. So those look like this if we're drawing these here. 1, 2, 3. And then here and here. How far away are all of those roots from the origin in the complex plane? Yeah, they're all exactly 3 units away. That is, they all live on the circle of radius 3 centered at the origin in the complex plane. And they're equally spaced. Do you see that? They're all exactly, if you know one root, you can get the others easily by just adding 120 degrees, right? Or 360 divided by 3. Or 2 pi divided by 3. You could just take one and add 2 pi over 3 to get the next one if you wanted. Because you know they're going to be equally spaced. That's not an accident here. You saw it happen with the 5th roots on the last one. Why is it true that when you take a cube root or a 5th root that you only get one real root? You get some other non-real roots, but you only get one of them is real.
Complex roots always come in pairs.
Okay, why?
Conjugates.
Okay, why, but can't you say that about an even root too? Don't they come in pairs too?
I mean, if it's like an even root, like for square root to like cube root, I mean, no, for the fourth root, like sixth root, then like even root.
Yeah, I mean, so the fifth root and the third root, I mean, really, I don't think you've ever explained why a fifth root or a third root has only one real solution, has only one real value. But we can actually, you certainly have never explained it using geometry, but now you can. You can kind of think, okay, well, it's of course going to be true if you have a regular pentagon, that if one vertex of the pentagon is on the real axis, no other one is, right? Just from the geometry of the picture. So does that mean that we can kind of do that analysis with fourth roots or something? Say you were solving z to the fourth equals 81. What do you know from your middle school algebra experiences? What are two solutions that you just would have said, even last year or something? You would have said 3 and -3. What are now, just by inspection, what are the other two solutions? 3 and -3, but what else? Yeah, up here, 3i and -3i. You expect, it's a fourth root. You expect 4 roots, and you expect them to be equally spaced 90 degrees apart in the complex plane. So there they are, and feel free, by the way, to check those algebraically. Just take 3i, for example, to the 4th power. You'll get 81. It'll be great. Yeah? And notice that for an even
Good
root,
afternoon, Richard Montgomery High School. Please
two of
pardon
them land on the real
for a
axis.
couple announcements about tomorrow, Wednesday, March 14th.
What about 6th
As
roots?
many of you are aware, I'm sure, student leaders across Montgomery County Public Schools have planned a demonstration in support of increased gun control legislation and to honor the 17 victims killed in the Parkland shooting. At Richard Montgomery, we want to support the academic and social emotional needs of our students while maintaining a safe and orderly learning
Please make a note of
environment.
this as you go to do
We
your homework
respect
tonight in the book.
the needs of our
You do
students
not need to do the
to
rest of the work.
advocate for themselves and for causes that are important to them. We are aware that some students in this school are planning on congregating prior to school and joining others from across the county in the national event in Washington, D.C. This is a reminder